Okay, all right. So now the online folks can hear me. Um, here's an overview of my presentation. I have some background discussions, then we'll talk about modeling the impact of summer drought on power grid, and we will discuss a case study in the extended PGM area, or mostly PGM plus CERC area, the southeastern region, and followed by concurrence in the future work. So background, throughout the presentations and discussions today, I think we have seen the discussion about the impacts of extreme events. This certainly our diagram looks a little different from the previous one, but it's pretty much same thing. Okay, so here the left diagram shows the primary extreme events at different countries worldwide. For example, Japan and Chile are mostly affected by earthquakes as extreme events, and Northern Africa, India, or Western Asia, China, mostly affected by extreme extreme drought, and also some country like Russia, South Southern America, mostly affected by flood. On the right diagram, it shows the share of power outage caused by natural shocks at different countries. That's the solid dots, and also the light dots shows the 50 U.S. States. The X coordinate is the GDP per capita, and the Y coordinate is the power outage due to natural extreme events. Well, there are some other studies showing, oh, is there any pattern between GDP versus extreme events? And well, that's a totally different topic. We're not going to talk about that. There are a lot of studies doing that. But here, just to show their extreme events are receiving increasing attention in the industry and also research community. So this one specifically shows the outage caused by natural shocks in the U.S. The left one shows the outages from different events like a storm, wildfire, and or other severe weather. The center diagram shows the case of outage from natural cause or versus non-natural cause. You can see that the natural cause is a significant portion. It's almost 50-50. Like for example, between 2000 2017, almost 55% of all recorded power outages being caused by natural shocks. So that's why we keep talking about extreme events and resiliency. Okay, it's something that you can't ignore. Okay, so this one further shows the historical data for over more than a century about the summer droughts in the U.S. So the top one shows the red one shows the drought, the extreme high weather, high temperature, versus the lower one. The bluish color shows the wet years. Okay, so you can see that it's being extreme summer hot has been happening in across the whole history. And this diagram specifically shows the 2007 summer drought case, especially in the southeastern U.S. Or eastern U.S. area. So that's some background discussion. So in this work, we will specifically talk about how to model the impact of the summer drought to power grid, including mostly generation and the load. Okay. So first, about the impact to generation. Specifically, we will study the thermal electric power plant capacity derating under extreme summer drought. So you may ask, what's the big deal for summer drought for thermal power plant? They just burn coal, right? Or maybe nuclear to produce the high temperature steam and then dry steam turbines, right? The thing is, the limiting factor is really the cooling system in a thermal power plant, because many times they use water, maybe a nearby river or nearby lake to cool the system. For example, here you see this one. Can you see this diagram? This steam. It's my icon. So here, this steam from the power plant will be cooled by cooling water. For example, the left one shows the cooling technology called once-through system, meaning the power plant will take water from a nearby water source, such as a river, okay, to cool the steam. And then that water will be released to the river, and that released water, usually temperature is higher. Okay, so in the case that there is, for example, summer drought, then you can get the enough water from the nearby river. Okay, certainly for some other cooling technology, like for power plants near the ocean, using ocean water as the cooling water, then you basically have infinite source, then you don't have that problem. So that type of plants are not at risk power plant during summer drought. However, if a power plant, thermal plant is using nearby water, a river as a cooling resource, then it will be at-risk plant during summer drought. Okay, and now that's a one-through cooling system. Another limiting factor is that, well, when you release the water back to the river, then there are regulations that your temperature, water temperature can be too high. Okay. Another cooling system is called a recirculating cooling system. Okay, or closed cycle cooling. So that's here. So basically, you take the cooling water and then going through a cooling tower and then recirculating that. That usually is less affected by the summer drought. But however, the air temperature here also affects the efficiency of and being a limiting factor. So here we list a few factors which could affect the usable capacity for thermal power plants, such as the available water supply, like stream flow of rivers and water temperature, and also federal and state regulation limit on the temperature of the discharged water, and also air temperature. That's mostly for the closed loop or recirculating cooling system. And here are a couple of equations, okay, to calculate the derating. So basically here, I'm not going to go through every variables there, but I can roughly show you that this one for the once-through cooling system, the thermal plant usable capacity is given by this and is related to available water temperature regulation, And then for the recirculating cooling system, the power plant usable capacity is affected by available water, water temperature, and air temperature, and humidity as well. So for the gas turbine, they're usually use the open air as a cooling system, but their turbine efficiency is affected by the temperature. So when the temperature is changed every degree Celsius, the efficiency will reduce by 0.7 to 1% because of a decreased efficiency. So we performed some verification study by selecting a few power plants in the PJM area, and here are the results. I can maybe briefly explain the curves. So the first, the green curve is the actual operational output for the thermal power plants. You can see that some of the curves not continuous. That's because of lack of EPA data, missing data. Okay, blue curve is the usable capacity calculated with regulation limits considered. Okay, so then we also we observe that the green curve, so the actual output, is at some days hours higher than the limit when we consider regulation requirement. So then if we ignore the regulation limits, then that's the orange curve. You can see that orange curve is perfectly always higher than the actual output. So this puzzled us, and we consider maybe during some extreme hours, the regulation maybe requirement may be relaxed. We talked with a few utility and plant engineers, and got that confirmed, especially during the past summer general meeting. So that's the interesting observation. So in our modeling, we ignored the regulation limit. So here is about the hydro generation derating model during summer drought. In plain language, it's pretty much related to the drought flow. So you see here, this equation here. Can you see this? So this drought generation is pretty much proportional to the drought flow, and we use this to calculate the hydro output at different states. We observed in the PJM and the CERC area, we observed several states with very strong correlation, like the R² value is greater than 0.7. And also we observed some value with very low R² value, which means the correlation is weak. That's we don't really have a strong data to support that. Our best estimation is that sometimes when you have an impound hydro plant, meaning with a reservoir, with a dam, during extreme summer drought, you really need the electricity. So some hydro plant with a dam reservoir may produce even more, because during summer peak, more electricity is needed. Okay, so anyway, in the PJM system, the hydro amount is small. Okay, so it's probably a lesser factor than the thermal plant derating model. So next, we also modeled the forced outage rate for generators during summer drought, and we extracted the data from NERC GATS database generation availability data system for all 20 megawatt and above units, and we observed the curves like this is from actually the GATS database. So what's the message here is that when the temperature is over like 30 degrees Celsius, then the forced outage rate start to increase dramatically. And certainly that's on the left side, that's for extreme cold system. It's related to our future study, but here we mostly care about this part. So the all in all, the effective forced outage rate of generators does increase quite a bit during extreme summer drought or during the heat waves. Okay. All right. Next, we studied the impact to load in the PJM and also circ system, circ without Florida actually. So index called temperature humidity index is applied. This the index we found from PJM's report. It's basically in plain language, if temperature is greater than 58 degree Fahrenheit, then we apply this equation which considers which consider humidity. Okay, if the temperature less than 58 degree Fahrenheit, then THI is basically is equal to temperature. Okay, so with this THI and also the load data, we can plot the THI versus daily load. So we can come up with pretty much piecewise linear curve for the load as different load zones demonstrate different piecewise linear curves. You can see that that's all for different load zone in PJM area. And I want to mention that first, 65 degrees seems to be a turning point, or between 65 and 70 degrees Fahrenheit, and load start to increase quite a bit. And below 65 degrees, it's kind of a load is a relatively small change or relatively constant. That's the reason probably because of HVAC up. When the degree is higher than 68, 67, then a lot of HVAC systems may be turned on. Okay, and also in some load zones, we may observe some saturation, like here. So the load kind of when the temperature is higher than some degree 85 or 90, so it may not increase as much as it increase at a lower temperature, probably because saturation of HVAC being turned on. Anyway, we applied the THI to model the load versus temperature. Well, the load versus THI, which is a unitless index. Okay. And with this, we can extrapolate the piecewise linear curve to identify the load under extreme summer drought. Okay, so next is a study in the what we call extended PJM area. That's basically PJM plus circ, but without Florida. Okay. So here is the process. We start with hydrological and the meteorological data, as well as the generation data. And then we calculate the at-risk power plant capacity derating model. And also we calculate the load projection under extreme summer drought. Then we perform the simulation study. So for the plant level stream flow data, and as well as the air temperature and the relative humidity data we can obtain from US GS, that's United States Geological Survey, and NOAA, National Oceanic and Atmospheric Administration, NOAA database. And here is power unit structure data for the extended PGM system. You can see that this is a projected generation mix at year 2025. We can see that primarily a lot of thermal power plant, like here, it's a combined cycle, and a lot of conventional steam, coal, and gas turbine, nuclear, hydro, and then this hydro 60%, PV, and wind is a small percentage. You see mostly thermal. So we performed the generation capacity derating for the whole extended PGM system. You can see that the orange dots are for the open cooling thermal power plant, and the red dots are for recirculating cooling thermal power plants. And we have also USGS gauging stations. If we don't find a gauging station at the thermal power plant, we find nearby the closest one and apply that data. Okay. And then we also using collected stream flow and hydrological data to calculate the daily usable capacity for each hydropower plant. So with the collected information, we obtain the derating results. So I want to explain a little bit about this three diagrams here. So we basically take the 2025 generation mix projection, and then I apply the weather data from 2005 to 2018. So combine that, then we produce the each yearly data. So for example, here, this box plot comes from the weather of 2005 plus the generation mix of projected 2025. So which means, what if the 2005 weather condition happens in the year 2025? So that basically shows the result for that. The reason we're doing this is to identify which year could be the worst year in the past 20 years. So the result is, the message is that this year, so this 2007, so if 2007 weather condition happens again in the year 2025, that will cause the worst consequence in terms of generation derating result. Okay. All right. So it actually, if you look at the meteorological data, 2007 and also 2012, they are very close. They're both very drought years. So that results makes sense. And in particular, you can see that the at-risk units with one through cooling system will be affected a lot more than the other system. It's like 15 to 55% capacity reduction in average. And for the recirculating cooling system, capacity reduction is 1 to 7%. However, we have more thermal plant with recirculating system, so that the absolute megawatt amount is still pretty significant. Okay, so the third one shows the derating results for gas turbine. It's 0 to 9.7% capacity reduction. Okay, so with this study, we pretty much identified 2007 as the extreme weather year we will use. Okay, and also we projected load in PGM and CERC, and for PGM is the load projection a little tricky, because if you look at the reports, the forecast in right in January 2020. That's right before pandemic. That's the blue curve. Okay, after 1 year, after pandemic, the PGM modified their load projection. So we basically applied this one, and that's once again, this is for normal summer peak load, summer load. And here, the for circuit system, we pretty much get the demand for projection and also normal summer peak. Then we apply the 2007 weather condition, meaning we assume the 2007 weather condition will happen again in 2025. That's basically the what if worst scenario. All right, then we send this, put it into a PCM production cost minimization model, and then we perform the study or dispatch study, and then identify the loss of load expectation, and which is for PGM system is 0.178 day per year, so which is violates the NERC standard. But certainly, we're not saying that, oh, in 2025, you will have a problem. It's basically, I think the point here is show the process to conduct a study, and certainly this results is based on a particular scenario, worst scenario, and also we didn't consider all the operational procedure like redispatch or the preventive and also all the corrective control actions. So there's a conclusion. So I think the important thing, especially for us, for power system engineers, all the derating model for thermal power plant and also hydropower plant is a pretty new experience to us. And we learn a lot through this process. And also the daily available capacity of all at-risk thermal power plant could be quite significant for if the 2007 summer drought happens again. Okay, so actually, if you check the PGM and CERC report back to 2007, you will find out that some power plants being shut down or being significantly reduced output during the drought drought days. Okay, I want to acknowledge the support of DOE, multiple offices, and also several national labs who worked in this project. So, good. My time is good, I guess.
Yeah, very good. Thank you so much, Fran. And we have time for 1 or 2 questions. If there is any questions from the audience.
Thank you for a very interesting model. So I didn't realize have you model? So we had another model presented by Bacon, modeling all the different basically events together, right? Like AC, AC running, and the drought and impact on the basically hydropower, and then on the thermal generation. Did we have that simulation, and how do you think that what are the limits of the grid? Is there any indication that we can calculate the limits of the grid in terms of temperature?
How? Oh, you mean how can we, with this model process, can we identify the limit? Yeah, we use a production cost minimization tool. Technically, we can identify that. For example, we can raise the load or HVAC load proportionally or following some conforming load pattern, and then till we for example, till some reliability index reaches the limit. That's pretty much, to my understanding, the limit of the grid can support at the current level. Yeah, but certainly things are evolving. There will be some transmission planning expansion project at the same time. Yeah.
Thank you.
Yeah. Mm. Okay.
Thank you so much. Any other question from the audience? Oh, we have one question here.
Do you have any like future work to study other types of generations, such as like turbines or idle flow units?
Yeah, very, very good question. Actually, we did model the impact or maybe a simple model for the derating for renewables. Right now, there are not a whole lot of data for that. It's pretty much you use a data-driven approach, like when for solar, when the temperature is higher than like 40 degrees Celsius, then capacity start to decrease a little bit. Then if it's higher than 55 Celsius, then it could be shut down. In the PGM system, even with the 2025 projection, not a whole lot of renewables. So we didn't see a whole lot of impact on that one. But for Western side, maybe more significant. Yeah, we did talk about the future works, checking using the same approach or processes to model the Western side with more renewables. And another work we have been doing is to model the extreme winter storm impact. Yeah, that will has some little different impact pattern to different generators. Yeah. Thank you.